Okay, so now let's go over some of the extra rules that we have about how to do the mathematics of vector quantities. All right, so let's say I'd like to take two vectors and add them. That's going to happen a lot. We're going to want to add vectors together. And so the very generic way to state that is I have two vectors, a plus b, and when I add them together, I get vector c. Of course, it's got to be a vector because I'm adding two vectors together. What this means in practice is that I take a plus b, and now I look at the components. So I look at each component of each vector, and I add that to the other vector to get my third vector. And so this would be ax plus bx. That's one component of c, so this would be cx. Just write it here like this. And then I have ay plus by. That's going to be the component cy. And I have az plus bz. And that is, of course, going to be cz. So now you can see, no pun intended, that we have a way of writing down for each component of each vector a simple rule that says this is how you add vectors. And the corollary of this is, of course, subtraction. A minus b is just the same. So it's ax minus bx, ay minus by, and az minus bz. And then these, of course, are the new values for c that you would get through subtraction. So add and subtract. Each of these gives us a unique new vector. Now, there are some important facts that we need to know. And that is that the rules of distribution, the rules of commutation apply to vectors in certain ways. So let's go through and understand something about the way we write things down. So I'm going to just rewrite this, for example, as how we add a and b results in c. We can also write that a is the difference between c and b. And so that matters, the directions of things matter. And so let's go through and just talk about graphically what it means to add and subtract two vectors. We can also state, so let's go through that. Let's think about how we represent vectors in two-dimensional space and how we add and subtract those vectors. So the way we do that is the following. Okay, so let's try and do that. Okay, so let's say I have first vector A, and I also have vector B. These two vectors, I want to add them together to get a resulting vector. And so what I can do with vectors is I can move them around on my two-dimensional space without any penalty. And so I'm going to move B to A, or A to B. So let's do that. Let's now shift A over, so here's A, I'm going to shift it to B, and this is now the result, which is A plus B, which is this vector right here, which I think we've defined as being C. Let me try and draw that slightly better. There we go. So this is C, A plus B. All right, so that's the addition in space, how we do this. And what you might notice is that I could reconfigure this to have A and B connected at their ends in the other way, and I would still get the same answer. The resulting vector would still be C. So, we can state that A plus B is equal to B plus A, with vectors, of course. So everybody adds together in a way that commutes. Now, what about subtraction? So, like I said, head to tail for addition. For subtraction, it's slightly different. So let's look at the subtraction of two vectors. Let's look at A minus B. Write this down. A minus B. What does that look like vectorially? All right, so let's draw our vector A again. And our vector B. And what I have to do in order to subtract these two vectors is if I have to move their tails in contact with each other. So I'm going to translate B over here. So there's my B. And now the connection between these two vectors is going to be the vector, the difference between these two vectors is the vector that points between A and B. And so this vector is the following. So A minus B is, give me color here, the vector that connects these two. This is A minus B. And as you can see, the arrow points towards the arrow of the first vector. So that's always the case. We're always going to work in conditions where when we subtract two vectors, the difference vector, the resultant vector, is going to point towards the first one that we have in our equation. The reason we say this is because when I subtract B from A, or A from B, I get a very different answer. I get a different vector. And so that vector looks like the following. Here's, for example, oops, sorry about that. To keep these colors straight. Here's B minus A. What does that look like? Well, let's move A to B. Yes, it is. It is the other vector. It is now this vector. Let's draw it here. As you can see, it points in a different direction. It's a different vector. And so with vectors, the important thing that you have to preserve is direction as well. So it's not just about the length of magnitude, it also is important to keep track of the direction. And so that is something we have to keep track of. Okay. All right. So now, let's talk a little bit about how that looks in practice. And we're going to have to get used to this because we do this quite often in physics. In fact, we're going to do it basically for every equation that we do. We're going to have to think about how things start and how things end. Because a lot of times we want to talk about dynamics, the movement of objects, and we have to know things that start and things that stop, and those quantities may be vectors. And so for example, let's just go back to our two-dimensional space, because it's easy to draw. And let's say we have a vector, we're going to call this one R2. We're going to call this vector R1. And I'm going to say that the difference between R2 minus R1 is going to point back towards R2. And I'm going to define this as being the change in R. Okay? And so this is delta R. That's the vector, delta R. Now, it's R2 relative to R1. That's how we say that in practice. Now this delta that I drew, this Greek letter here, we're going to use that a lot. So delta is a letter from the Greek alphabet that you're going to use a lot. It's delta. It's a capital delta. And it represents in physics the idea of a change in something. Change in lots of different types of things. Change in mass, change in position, change in velocity, change in momentum, change in force, change in time. We write them all with deltas. And so, like I said, the quantity delta R, if we're talking about things that start and stop, we're going to say that's the R of the final configuration minus the R of the initial configuration. We could also do this for time. Delta T would be the time initial, or I'm sorry, time final minus the time initial. And I can shorten that by saying R sub F minus R sub I, or T sub F minus T sub I. And that's how we're going to represent things in physics, by changing. Okay. All right. So that's going to be it for vectors for now. We're going to move into physics for the next lecture.